Hello, my name is Malia Kinsey. I'll be discussing Internet of Vehicles. Simple outline, I'll describe its characteristics, its architecture, the importance of IOV, its applications, some of its challenges, and then introduce social Internet of Vehicles. So, different types of devices are created to help maintain safety or ease of operating vehicles. These devices are cooperative, interactive, and well-informed to pave the way for supporting road safety, smart transportations, location-dependent services, and in-vehicle internet access. IoT, or Internet of Things, is known as a global network connecting smart objects and enabling them to communicate with each other. When these smart objects are connected over internet and are also vehicles, then Internet of Vehicles, IOV, is introduced. Another name of IOV is connected cars, which can be defined as the presence of devices in an automobile that connect the devices to other devices within the vehicles. A vehicle, in this sense, becomes a sensor platform that gains information from its surrounding environment and other vehicles. The main focus of bringing wireless connectivity to vehicles is the urgent need to improve efficiency and the safety of road transportation systems. IOV also focuses on alleviating traffic congestions. It is used to solve several problems that are faced in VA-nets. Some of these problems that are faced are scalability, ubiquity, and lack of coordination between vehicles. One of IOV functionality include enabling cars using modern electronics and integration of the information to help maintain traffic flow. It also helps perform more effective fleet management and accident avoidance. The characteristics of Internet of Vehicles. IOV has several different communication types that help characterize its functionality and structure. The types are vehicle to vehicle, vehicle to infrastructure, vehicle to human, vehicle to sensor, and vehicle to roadside units. V2V communication. This has the ability to wirelessly exchange information about the speed and position of surrounding vehicles. This is useful because it helps to avoid crashes and provides the ease of traffic congestions. Information generated by vehicles, sensors, control system, or passengers can be effectively dispersed among other vehicles in proximity and to vehicles multiple hops away in VNX. By using an inter-vehicle wireless communication link, a variety of active road safety applications and infotainment applications are enabled. V2V communication allows vehicles to broadcast and receive omnidirectional messages. This communication can increase the performances of vehicle safety systems. It also provides drivers the tools needed to anticipate potential crashes. Simply, the driver might be told to brake now or risk an accident. The biggest challenge with this communication type is the environment, such as in an urban area, the line of sight of path of V2V is often blocked by buildings at intersections. V2I communication. This is a wireless exchange of data between vehicles and road infrastructure. Some infrastructure components are lane markings, road signs, and traffic lights. It captures vehicle-generated traffic data. It wirelessly provides information such as advisories from the infrastructure to the vehicle that informs the driver of safety, mobility, or environmental related conditions. Devices using V2I helps improve roadways, mobility, and safety. For example, pavement lane markings that are visible to humans and machines in any road condition. Example, these markings work with automated vehicle sensors to detect lines outside the vision-based spectrum. It improves lane detection and traffic safety in extreme weather conditions. V2R communication. This type of communication allows vehicle to communicate with fixed infrastructures alongside of the road, providing user communication and information services. It would include traffic signal control systems, parking information, and weather reports. The warning messages in V2R communication are sent to roadside units first, and then it'll be broadcasted by RSUs, which is roadside units, to all other vehicles in range. V2H communication consists of introducing additional visual cues such as lights, and this communication type is specifically important to autonomous vehicles. Some other characteristics of VIO-V is that it enhances driving aids by furthering the vehicle artificial intelligence awareness of other vehicles around them. It is connected in an ad hoc network which uses vehicles as a node. Each entity within the network can connect to the internet. By connecting to the internet, it brings the luxury of sharing information between different components. Internet connection also provides flexibility of expanding the scale of the network. So, the architecture of VIO-V. The objective of this architecture is to be open and flexible, capable to include different technologies such as cloud computing and mobile edge computing. The architecture of VIO-V is designed into 5 layers, which is displayed in this image. This image explains the functionalities of each layer and the representations of them. I will further explain each of those. The first layer, perception, it is represented by different types of sensors. The main responsibility of a layer is to gather information regarding vehicle traffic environment and devices. The information includes speed, direction, acceleration, position, engine condition, and travel documents. This information relates to vehicle, on-road vehicle density, and weather condition. The main issue of this layer is the collection of information and efficient cost and energy. So more in depth of the perception layer. It is within a vehicle and contains all sensors that gather environmental data and detect specific events of interest. Some examples are driving patterns, environmental condition, and vehicle situations. In terms of its functions, the perception layer corresponds to the PHY layer. Its main functionality is to gather information in vehicle, traffic environment, and devices. This layer contains RFID, which is radio frequency identification, which is a form of wireless communication that helps identify an object or person. It also contains the following to help receive specific information, such as satellite positioning perception, road environment perception, vehicle position perception, and car object perception. The second layer, coordination layer, is represented by a virtual universal network coordination model for different networks, such as Wi-Fi or Wave or LTE. One of the main responsibilities is to process the different structured information received from these networks. Cooperation among these different types of network is the main concern when providing reliable network connectivity. From the picture, this layer also provides secure transportation of information. So more in depth, it's also could be called a network layer, which is the communication layer ensuring connectivity to communication networks. This layer helps support the different communication types. The main functionality includes creating a unified structure with identification capabilities for each type of network. Some more challenges that the layer faces is the need for reliable network connectivity and cooperation among different types of networks. The third layer, the artificial intelligence layer, is represented by the virtual cloud infrastructure. This layer is responsible for storing, processing, and analyzing information received. It is responsible for decision-making based on critical analysis. One of the main concerns is due to the number of services offered in a cloud environment. Service management causes problems when exclusive and dedicated services are required. The fourth layer, which is the application layer, includes the smart applications that range from traffic safety to infotainment. It includes statistical tools, support for storage, and processing infrastructure. It is responsible for providing smart services to end users. It also provides end users application usage data to the business layer. So the main responsibilities for this layer is storage, analysis, processing, and decision-making about different risk situations. Some of these risk situations include traffic congestions or bad weather. It is represented by smart apps, traffic safety, and efficiency. The last layer, business layer, is represented by the operational management model of IOV. The main responsibility is to foresight strategies for the development of businesses. This is done based on the application usage data and statistical analysis of the data. Another responsibility includes decision-making related to economic investment. So why is IOV important? What roles does it play? And why is it necessary? The Internet of Vehicles is very important now in society since technology is expanding. The main target domain of IOV includes vehicles, driving, and safety. It can also focus on urban traffic management and automobile production, such as road infrastructure, construction, and repair, or vehicle insurance. IOV is also important for autonomous vehicles as they communicate instantly to other vehicles around them. By allowing instant communication, it makes it easier for notification of such like braking, changing lanes, or even turning. This will help ensure smooth and safe transportation between autonomous vehicles. So one of the main importance of IOV is traffic management. Majority of the advices created for IOV are to help with traffic management and safety control. So for traffic management, there are 4 specific types of communication. Communication between vehicle and vehicle owners, V2V, communication between vehicles and centralized servers, and then communication between servers and third parties. So the first type of communication includes attributes of vehicles such as speed and fuel levels that are directly reported back to the user. This report is normally when the vehicle is in use to enable the user to receive active updates when a vehicle is not being used, and onboard processing is necessary. The second type of communication, vehicle to vehicle, is known. It involves sharing of data such as proximity of vehicles, monitoring of immediate surroundings of vehicles, speed of vehicles within a radius, and accidental information. Proximity of vehicles are crucial in avoiding accidents. Knowing the speed of surrounding vehicles help in ensuing a warning to other nearby vehicles, which also helps in preventing accidents or changes or damage. Third, communication between vehicles and centralized servers involve data monitoring from the vehicle being relayed to the nearest communication node through an onboard computer. From here, the node communicates the data through a satellite to the communication node of the server. This server potentially monitors breaches that could possibly happen. The last communication primary concerns are the data regarding vehicular collisions, temperature spikes, and theft. When these data are reported from the onboard processor to the server, they are then forwarded to respective third parties, such as police officers or ambulances. So there are quite a few advantages using IOV. So with traffic control, data is relayed directly to the traffic signal. This helps decide which lane to clear faster, or how much time a green signal is needed to be allocated for each lane. And then human proximity detection. This uses the proximity sensors on board to detect the body temperatures of humans on the road or nearby pavements. Due to visibility issues at night, this could really help reduce fatal accidents. Sensors detect human presence on a road and immediately either reduce the speed of a vehicle or, notify them. It could also apply emergency brakes depending on the proximity of the vehicle to the human being. Then you have theft avoidance, which is designed to identify keyless entries, breaking the window panes, or even forceful startups. The processor will immediately lock down the vehicle and prevent it from starting up. There's accident avoidance, which uses vehicle-to-vehicle communication. This helps detect when vehicles are either going to collide or if a single vehicle just simply loses control while driving. Then there's emergency response, which is when a vehicle undergoes collision or detects a collision is nearby. Then this is when ambulances are immediately sent and with information on the exact GPS coordinates of the accident site. One of the last advantages is basic attributes of vehicles that are monitored and reported back to the user. Among these advantages, there's also disadvantages. Security is the number one concern with traffic management of IOV. Hackers pose a major threat to the system, being that there are a number of vehicles on the road and a number of links to a number of nodes all connected to a central server. A single loophole of the nodes may result in the exploitation and crash the entire system. And then another concern is the failure of networks. Due to the huge number of vehicles on the road, servers and processors must be able to handle them and handle the load. It could potentially slow the networks or even cause it to crash, stopping the communication. So, the applications of IOV. There are plenty of applications. These applications could be divided into different categories. The two main categories I'll be dividing these applications in are safety management and business management. So with safety management, you can further divide them into safety, navigation, diagnostics, and remote telematics. With safety, you have lane changing warnings, automatic braking, automatic speed control, and there's several others. Navigation, you have real-time traffic, locating a parked car, speeding evidence. Diagnostics, there's service spots detection, self-repair, car usage checking. And then remote telematics, you have remote locking, fuel usage optimizations, and then car surveillance. So safe driving refers to the cooperative collision avoidance systems that uses sensors to detect imminent collision and provides warning to the drivers. It could involve periodic status messages and emergent messages that are triggered by emergency events, such as traffic jams, accidents, and road conditions. Some devices include automatic braking, wrong way driver warning, and overtaking warning, and emergency calls. Traffic control apps will bring about a fundamental change to urban congestion management, transport and logistics, urban traffic, and our collective lifestyle. Applications handling traffic control will help maintain balance between populated areas such as traffic light controls, traffic such as traffic light controls. Traffic enforcement applications can implement speeding warnings based on vehicle networking. These applications can monitor illegal driving behavior, and it can ease traffic congestions to avoid traffic accidents. And you also have the crash response applications. This makes it easier for emergency vehicles to receive accurate information quickly. Connected cars will be able to automatically send real-time data about a crash along with the vehicle location to emergency teams. Vehicles will be able to report accidents and send these GPS locations, as mentioned before, in these apps. Then you have the business management of applications. You have insurance, infotainment, car sharing, and just general applications. So insurance, you have, group family insurance, and then usage-based insurance. Infotainment, which is, your entertainment. You have Wi-Fi vehicles, music downloading, social media sites, just different entertainment apps that you use. Car sharing, your carpooling, group parking, booking, and then other like mobile toll payments such as, the SunPass. And then you have cloud service. So some convenience services apps can provide transportation agency with improved real-time traffic transmit and parking data, which makes it easier to manage transportation systems for reduced traffic congestions. These applications have the ability to remotely access a car, making it possible services for remote door unlocking or stolen vehicle recovery. And then for the infotainment apps, connected cars can provide online and vehicle entertainment options that provide streaming music and information through the dashboard. Some applications and features include social media streaming, connected drive, location sharing, and even connection to the address book. Now, the challenges and issues of IOV. There's several that IOV faces, being that it's a huge network. So some general challenges are to develop advanced network model and service model of human vehicle and enhance communication abilities. Some other issues includes big data, which is due to the large number of connected vehicles that are out there. This is a critical issue because of the concern with processing and storage of big data. And then you have security and privacy. This issue is because IOV is an open public network, which could lead to being target for intrusions or cyber attacks. This could result in physical damages or privacy leaks or hacks. Reliability comes into play because the devices used, they're not always reliable. You're using internet connectivity, you're using wireless connectivity. We all know that wireless sometimes it shuts down. Vehicles, sensors, and network hardware, it can malfunction at any time. Malfunctioning will lead to incorrect data and or faulty communication between the different communication nodes. And you have mobility problems, which occurs in such a diverse network. Since vehicles are moving fast and network topology changes continuously, it's a challenge to keep the nodes connected and provide them with resources to transmit in real time. Among these general issues, there's technical issues, such as localization privacy, accuracy, and then location verification. So location privacy is basically having a highly MA-net environment. Vehicle communications are based on broadcast messages and periodic beaconing information that is just sent and it's just broadcast. These messages typically include location, velocity, direction, acceleration, and the vehicle type. The most challenging task is to keep this privacy. Location privacy becomes a main concern, and vehicles must utilize location information for communication without actually exposing the information itself, like their location or where they're going, due to it being such an open network. And then you have localization accuracy. The accuracy requirement in vehicular communication environments makes it challenging for accurate localization. The requirement is higher than the accuracy provided by GPS-based localization. There are 3 issues to address to fulfill the accuracy requirements versus what, a GPS-based localization actually provides. So the first issue you have is a GPS-based localization provides accuracy of 5 meters, whereas the accuracy requirement is actually 50 centimeters. Then you have the second, which is it does not take speed of the objects into consideration, so that accuracy could be off. The last is the quality of GPS signal in such areas and environments such as an urban area where it's more dense of traffic. Then you have location verification. This is a challenging problem due to the absence of trusted authority in vehicular communication. There are certain techniques used for location verification that includes certain issues. The cost of infrastructure and directional antenna includes limitations of range based on vehicular environments. Another issue is the overload involvement and the beaconing approach of messages. And then the last one is the untrustworthy neighbors. You don't know what they're saying out and whether it's accurate information or not. Then we come to SIOV, which is Social Internet of Vehicles. The communication types interconnectivity creates a social network where the participants are intelligent objects rather than human beings. This leads to the emergence of Social Internet of Vehicles. In SIOV, entities socialize with each other by sharing information of common interest, such as, traffic information or weather conditions. SIOV is not limited to only vehicles and can include drivers, passengers, and infrastructure. It's very similar to IOV, of course. Social Internet of Things is a network of intelligent objects that have social interactions. SIOV is where the objects are vehicles. SIOV describes both the social interactions among vehicles and drivers. It is a term used to represent when vehicles build and manage their own social network. It is used to recommend location, profile-based services, vehicles navigation and monitoring, managing network access, targeted advising, and more. When a vehicle is part of SIOV, it must build and position its network in order to accomplish user goals. A vehicle's social network is described as social interaction among vehicles that communicate autonomously and exchange information relevant to traffic. So, some key components of SIOV. There are several factors that are dependent upon SIOV, such as context, connection type, network structure, and nature of application, and also environment. The core objective of SIOV is enabling the social relationships among various entities. In SIOV, a vehicle maintains that social relationship list of other vehicles and communications to the user using onboard units, or OBU, that is installed in that vehicle. This is used for sending and receiving information. A key aspect of SIOV is centrality. This assists in providing measure for finding entities that play a major role for vehicles. It also facilitates efficient information dissemination by enabling the entities to act as a relay node. Another key aspect for socialization of entities is clustering. It categorizes vehicles based on parameters like interest of the vehicles, speed, location, and density. An advantage of clustering is handling of broadcast storm problems and improving bit error rate relationships. And then the relationships are, they're built on mutual interests. So with SIOV, there's several applications. I'm only going to speak on 3. RotoSpeak, it is a voice chatting system that allows computers to dynamically enter vehicle networks on the fly and exchange informations in between. Another application is NaviTweet. This application incorporates the driver's preferences into the navigator's route calculation using traffic voice tweets. The last application mentioned is Caravan Track. This is a similar application that allows drivers to share mobility data among cluster of cars. So with SIOV as well, there's different challenges that they face, such as security, privacy, trust management, and managing those social relationships. Along with those, SIOV also lacks a standard architecture. A requirement for SIOV is scalability. It provides information and resource-rich environment that can offer on-demand services to different components. Due to this dynamic expansions, a scalable SIOV causes many issues and problems. It is difficult to prevent the scale of the network as various components enters and leaves the networks. SIOV systems they're highly dynamic in nature. This is because of their mobile entities, such as vehicles that have a tendency of changing their neighboring nodes often. Being dynamic, it makes it hard to build a trusting relationship since the nodes are always changing. The reputation of new vehicles will have to constantly update, making it hard to become part of SIOV's architecture. There are several other factors that makes it challenging for SIOV to have a foundation environment. But some of the general issues that SIOV faces deals with the privacy. There's threats, DOS attacks, false message injections, malware, impersonation attacks, and then you have your trust issues of SIOV due to it constantly changing. So that is all. Due to the increased usage of technology and internet today, IOV has been a main talk and increasing in the automotive industry. It's used more now because of this increase. So thank you, and sorry I couldn't be there today.